Now, after that last video, you might be pretty confused about the whole shape of the graph with the derivative. And in this video, I'd like to go over a real example of what I was talking about, because it's a lot of new material and it's pretty confusing. So I'm going to go ahead and start out with this function y equals 2x to the fourth minus 4x squared plus 1. And let's just go ahead and take the first two derivatives. The first derivative here, we're going to get 8x cubed minus 8x. That's going to go away. The plus 1 is going to go away. And the second derivative is going to equal 24x squared minus 8. So let's set these equal to 0 and see what we get. I'm going to copy these over here so that I can manipulate them. And so the point of what we're doing here is we have to be able to tell where we have critical points and what the graph is going to look like without having the graph given to us using only calculus. So let's set this equal to 0, set this equal to 0, and solve. I'll go ahead and move this up. Oh, I'm in a little trouble here. Okay, I'll move this up. So we say we can factor this. So we get 8x squared minus, actually, here, let me rewrite this. We can factor an 8 and an x out. So we get x squared minus 1 equals 0. And we end up with 8x times x plus 1 times x minus 1. If we factor this, x squared minus 1. Set this equal to 0. Give us a little more room here. So now we see the critical points occur at x equals 0, 1, and negative 1. And let's hold on to this. So in this next one, we can divide by 8, just get the 8 out of there. So we get 3x squared. Because the 8 is a constant, we can just take that out. Now, well, let's just go ahead and do this. We'll move the 1 over, so we get 3x squared equals 1. Divide by 3. Go over here. So x squared equals 1/3. And x equals radical 1/3. Whoop, here, let me fix this. There we go. And finally, we have to add the plus and minus, because if we go in the reverse direction, squaring this, either the positive or negative goes away. So we have all the critical points we need, and so we can check these points for the first derivative. At these points, it goes from either negative to positive or positive to negative, and the slope is equal to 0. So because the slope is 0 at these points, there's a chance that we'll find a local extreme. We know we'll find a local extreme, and possibly, or it depends on what this graph looks like with the second derivative. So these are possible local extreme values. Here, at negative radical 1/3 and positive radical 1/3, we're going to see we're probably going to see a change in concavity. So I've got something here that might come in handy, the TI-83. I saw this used on the Khan Academy, so I thought this might be helpful. So let's see what we would actually do in our calculator in real life. Now, if we want to graph this function, we'll see how it ends up looking. So we have 2x to the fourth minus 4x squared plus 1. And let's see what this looks like. Alright, if we want to zoom in here, let's see how this matches up with, okay, I'll do this. Zoom in. I'm going to zoom in a couple times here until, okay, that looks good. So let's match up what we see in this graph on our calculator with what we've drawn out here. So our first derivative has critical points at 0, 1, and negative 1. I'm going to quickly take a little screenshot of this here so we can play with it inside of Paint. Alright, there we go. So I'm going to bring these down. Whoop. So this is our first derivative here. And this is our second. Those are our critical points. So at 0, 1, and negative 1, we're going to expect local extremes. And what we see in our calculator is this is actually completely true. This is 0. We have an extreme there. 1 and negative 1. And so if we look between 0 and 1, if we plug that into the first derivative, if you go from 0 to 1 on this function, or you plug in any point from inside this area on here, you're going to get a negative derivative, one that's going downwards. And so we know that it decreases from this point to this point. And if we plug in a value from that section into the second derivative, we see that it's concave down. Now, another thing I'd like to point out here is that we see a change in concavity at one point on the graph. It turns out that, at 2 points on the graph. If you look here at these 2 points, it might be hard to see, but from this area on the left here, we have something that kind of looks like this. It comes up here, comes back down, back up. So at this point right here, the concavity is changing, and at this point right here, the concavity is changing. And so, see right here, before there, we have this upward slope. This is our concave up, but then once we hit that point, it goes concave down. And then once we hit the second point, it goes back to concave up. And the point exactly where it switches, that point, inflection point, where the concavity changes, we see from the second derivative is actually plus and minus radical 1/3. Now, what's great about what we've done here is we've found the exact answer for these 2 points where the inflection changed. Now, if you were to do this on the calculator, let me grab this. If you're going to go in the calculator and trace it, then use the, I haven't done this in a little while, so forgive me. I think you go calc. Yeah, if you want to solve these zeros, you have to do bounds there. And let's do a guess right about there. And see, we get an approximate value, negative 0.5411961. But if we do negative radical 1 divided by 3, we get the same thing, but this is our exact answer. And so, I'll close out of this now. Hopefully, this kind of sheds some light into why we use derivatives. Using the first one shows us where it's decreasing and increasing, and we see that at 3 points here it changes direction. We found those by setting the first derivative equal to 0. So at -1, 0, and 1, it goes from decreasing to increasing, back to then decreasing, then back to increasing. And then at 2 points the concavity changes, so it goes from concave up to concave down, back to concave up. So I hope that you found this video helpful, and I hope that it shed some light onto how to actually use this shape of the graph idea that I gave in the previous video. So in the next one, we're going to be looking at some differential equations, which can be pretty annoying, but hopefully they'll make sense. And if you have any questions about these or a specific example you'd like me to go over, leave a comment and I'll be sure to get back to you. Alright, thanks for watching and goodbye.